Pre-flight 101, the course that will give you wings. 6. Performance and envelope limitations. 6.2. Performance, cruise and landing. This lesson is similar to the previous one. We will be taking a look at the use of performance charts for the phases of cruise and landing. How was the exercise from the previous lessons? Was it easy? Well, this lesson is very similar to the last one. So if you want to take a look back at the last section, especially at the part where I taught you to read charts, you can do it now. That way this lesson will become way easier. Anyway, let's get started. The chart you can see now in the screen is the cruise phase chart. This one is used to calculate the load, speed, and fuel consumption for a certain altitude and engine RPM for certain atmospheric conditions. Okay, this chart is gonna work the exact same way as the other ones we used. We are going to be using the same 5 steps, and basically it's going to be working the same way with the same working principles. Anyway, let's get started with the examples. The example number 1, you're doing a cruise at 6,000 feet, 2,550 pounds of weight. Mixture is leaned as appropriate. ISA minus 3 degrees. And for a test, for a true airspeed of 122 knots, find an RPM required and the fuel consumption. We're gonna set that in red, and also find the RPM and resulting true airspeed from a consumption of 8.2 gallons, and that's going to be done in green. So basically there are 2 examples in one. Anyway, let's get started with the charts. First thing, we're going to read cruise performance. Are we talking about a cruise? Yes, we're talking about a cruise. Then we're in the correct chart. Second, we're talking about conditions. 2,550 pounds. Yes, that's correct. Recommended lean mixture at all altitudes. Yes, mixture is lean as appropriate. Refer to section 4, cruise. Okay, normal procedures, cruise. If I ever have a doubt of how things are working, I should go to that POH section. Anyway, now let's get working with the chart. First thing I'm going to do is look for the part of the chart that talks about the pressure altitude I'm at. As you can see here, it says 1 out of 2. This is because the other one is going to be working for 8,000 feet, 10,000 feet, and 12,000 feet. Okay, we are using this one because we are using 6,000. Now, cruise at 6,000 feet. And we are looking for a TAS of 122. Find the RPM required and fuel consumption required. That's going to come up in red. So, standard temperature. Should I use 20 degrees below the standard? Should I use 20 above? Should I use standard? It's a standard -3. However, I cannot use 20 below standard. So I'm going to be using standard temperature. Remember, we always gonna be using the most restrictive. Okay? So, let's keep working at that. We're going to look for that speed, or something that looks like the speed we were looking for. So in this square, that is the data we're going to be using, we're going to be looking for 122. Not here, 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 here. No. We're looking for 6,000 feet at standard temperature 122. So with this speed, we're going to be doing this percentage of the brake horsepower and these gallons per hour, so this fuel mileage. So for a task of 122 knots, we are going to be doing RPM of 2650, and our gallons per hour are going to be 10.4 gallons an hour. So from that speed, as you can see, you're going to be able to get most of the data. Okay, let's go now with the second example. They give us a fuel consumption of 8.2, and they are asking for RPM and resulting true speed. When can I use this example? Well, imagine you want to burn the less fuel possible, or you want to burn a maximum amount of fuel per hour, and that amount of fuel per hour is 8.2. For planning purposes, for 8.2, you might want to know which is the best altitude for you. Imagine, here with 8.2, I'm going to be going at 109 knots with 2400 APM. And here with barely less, 8.5, 8.2, I'm going to be doing more or less the exact same speed with the exact same RPM. So I can be choosing from different altitudes, I can be choosing from different airspeeds. I'm just basically getting the best performance out of my aircraft by setting this fixed 8.2 value. So how do we do it? The way to start is exactly the same. Go to the standard temperature and go to 6,000 feet. Okay, we get this 6,000 feet because we are cruising at 6,000 feet. We get that standard temperature because it's the most restrictive. Okay, -3 degrees from ISA. We're gonna be taking it as standard temperature. Later, look for the data that you were looking for inside this square. So 8.2 or something that looks like 8.2. In this case, we have 8.2 here. Okay, so 8.2. And now we're looking for the RPM resulting and the true airspeed. So the true airspeed should be around here. Okay, and the RPM required are going to be 2400. There and there. So that's how you work with the table. The next steps would be step 4 and step 5. In this case, we don't have the notes, so we don't have to do those steps. That's how you use a cruise chart. So, was that easy? I'm pretty sure it was. This is the last performance chart we are going to be seeing today, and basically in this course. This is the landing performance charts. It's going to allow us to calculate how much runway we're going to be using or we're going to need to safely land depending on the conditions. As you can see, it looks pretty similar to the takeoff chart, and basically we use it exactly the same way. So we're going to run straight into the example number 1. Landing at a pressure altitude of 1,990 feet with an outside air temperature of 13 degrees Celsius, 10 knots of headwind, dry paved runway, and all the parameters standard. We need to get those those landing distances. So first thing I'm going to do, read up the short field landing distance at 2,550 pounds. Good, I'm using the correct chart. Perfect. Conditions, flaps 30, good. All of the parameters standard is gonna allow us to actually meet all the conditions. Power off, yes, if I'm landing, I'm probably gonna cut the power at some point. Maximum braking, yeah, well, not maximum, but you know, I'm gonna be, yes, for calculation purposes, it's gonna be maximum braking. For the rest, we don't use really maximum braking if it's not necessary. I mean, aircraft brakes are really expensive. We don't want to brake something, so we're just gonna brake softly. Paved, level, dry runway. Yes, dry, paved runway, perfect. Zero wind, okay. Yes, we have 10 knots of headwind, so that's probably gonna become a change at some point. speed at 50 feet, 61 knots. So this is what you are aiming for. At 50 feet, you should be flying at around 61 knots. So these performance calculations are correct. So let's go with step 3. Let's take a look at the chart. 2000 feet. Why 2000 feet? Well, your pressure altitude, as we said before, is 1990 feet. So we're going to use the most restrictive. In this case, it's pretty clear, 2000. The next thing we're going to do, you tell me. Exactly. We're going to be getting the temperature. So am I going to get 10, 20, 40? Exactly. For an outside temperature of 13 degrees, I'm going to be getting 20 degrees because it's the most restrictive, right? Good. So I'm getting those two distances, 630 feet of ground roll and 1,420 feet of landing distance, actual landing distance from 50 feet. So basically, I could land in 63 meters. That's pretty good. That's actually a good distance. Anyway, so those are my final distances, right? No, I have to actually work the notes now. Let's see what we see. Anyway, one short field technique as specified in section 4. Okay. Decrease distance is 10% for each 9 knots of headwind. For operation with tailwind up to 10 knots, increase distances by 10% for each 2 knots. Exactly the same as with the takeoff. Okay. Here it says decrease distance is 10% for each 9 knots of headwind. If I have 10 knots of headwind, how much should I decrease the distance? Exactly, a 10% for each 9 knots. Until I don't have 18 knots, I cannot apply the next correction. So if I have 10, I can only apply 10%. Good. Let's keep going with the next one. 3. For operation on dry grass runway, increase distances by 45%. Well, we are luckily in a dry paved runway, but as you can see, landing on grass actually increases our landing distance on the ground by almost 50%. So just think about that when you're going to be landing on a grass strip. 4. If landing with flaps up, increase the approach speed by 9 knots and allow for 35 longer distances. So if your flaps are not down, you're going to have to actually add some distance. In this case, our parameters are standard. The standard landing, as we will be seeing in the normal procedure section, is with flaps down, so we do not have to add any more runway to that. And that's how it is, pretty easy. Step 5, checking that everything is correct. Short field landing distance. Yes, we use the correct thing. Good. So our calculations are correct. Perfect. We finished with this one. So yeah, that was it. You can calculate now performance for cruise and landing. Just like in the previous lesson, here I'm gonna leave you these conditions. I'm gonna leave you this chart and that example number 1, and this way you should be practicing on your own and getting better and better and faster and actually preparing your takeoff and landing calculations. Anyway, see you in the next one. We're going to be talking about limitations. So, to sum up this lesson, basically we talked about landing performance, we talked about cruise performance. We saw that basically all the charts are going to be being used the same way. So practice, try to use them the most you can. Always be careful, follow the 5 steps, follow my tips, and you will see that the charts are actually really easy to understand. Anyway, as I said before, we're going to be talking limitations in the next section. Stay with me and keep learning. See you on the next one.